used some concepts before. And linear algebra is defined on vector. It has two important components. First, the vector space, and another is linear transforms. Vector space, I usually use big numbers. Is a way to denote. Use the LVW to denote the linear transform from the vector space from V to W. And if W is equal V, shorter as this one, LV. And linear transforms have some properties such as additives and homogeneous. And before that, I have proved that we can use the matrix to express linear transforms based on some specific basis. This one. We have divided basis which is the independent and I have dimension as the vector space. And if the transform the space is W1, Wn, now I use this matrix to denote the transforms. Of this V and having the transform the vector space L, we can use this to denote this transform. And it depends on the transforms and the basis you choose. And I have already proved that we can choose some specifics for a complex vector space. We can choose if V is equal W. Yeah, in this term. We call it V1, V2, Vn, and this becomes a square matrix. And if they need a complex vector space, we can choose some specific basis to make this matrix upper triangle, which means that A can be this form or is 0. We can choose this basis. And we also studied the inner product space and defined the inner product is this one. Have some properties we just learned in math class. And based on the inner product, I defined the joint. I don't know how to call it. A joint operator, which means that for a linear function, we define this operator based on inner product, and if W is first we choose the W, and this is the linear function of V, because this is linear and the inner product is linear, so this is a linear function. And I prove that linear function can have this form for some specific V can be denoted. I have proved. So we use this director to use this operator to denote the unique operator to one. This two is different because W, we use U. U and W are in the same vector space, and this is another mapping to the V space, and this one defined. And I also defined a self-joint operator, which is that two operators are the same. And if it's normal, which means that this one is normal. It's very associated with matrix transforms. And if for complex vector space, if the operator is normal, we can decompose the operator and the matrix as a diagonal matrix. I have proved it's a spectral decomposition theorem. And if the real space and satisfy this function, it also can decompose the diagonal matrix. And the condition is sufficient and necessary, both each direction. And I also mentioned in last class is two important operator. The first operator is non-negative. Is this operator? It's defined as this one, and T is self-joined, which means T is equal to T star, and this matrix and it defines some like square root, and non-negative. It has a unique square root, can be defined as this one. And also define, also mentioned last class in asymmetric operator. So like this one. Use S to denote. For each operator in the vector space have this property. We call the S is asymmetric operator. That's what I talked mini talk before on this one from the beginning. We know that if the operator is self-joined for real space, and if it's normal in the complex space, we can decompose that this diagonal. This is very beautiful because for each vector space we choose, it can be decomposed like this one. It's the diagonal, the scatter in the diagonal is the eigenvalue, and we can decompose the whole space in one dimension, and it's easy to study for us to study. But for the general operator, it's another story. We cannot make the general matrix or general vector just based on the vector, eigenvector, and the matrix like diagonal. But today, I will deep research about how to decompose the general matrix. And it's by two parts, and it depends on the vector is complex or real. As a matter of fact, the real is complex. I think I will mention about this one. If you have interest, we can discuss. And in the next, I focus on the complex vector space and how can we decompose the whole vector space. As said before, for each vector, complex vectors operator, it has at least one eigenvector. I have proved, and as a matter of fact, if we count the double or prove it can be expressed as this one for some species vector. So it has n for the complex vector, it has n scalar n eigenvalues, and they may be the same in the diagonal, and all different or same. And first, I will define an eigenvector called the general eigenvector, which is for some specific eigenvalue. T. It's defined like this. G is integer number and bigger than 0. It's the political integers. G is a political integer or natural numbers. If V is not equal to 0 vector, and we define this as the general vector. If G is 1, this is the eigenvector, the normal eigenvector, but it's bigger than 1. Maybe you can another vector, because all of this is eigenvector. So the normal eigenvector is belong to the general eigenvector.
So is this called general eigenvalue also? Like
no general eigenvalue, just the eigenvector.
So, like, for example, can we have condition like when only j equal to 2, we have to be satisfied, but j equal to 1 is not satisfied?
J is equal to 1?
Yeah, because usually we have like t minus lambda I v is equal to 0. Like, yeah, this is the argument. Then lambda is the eigenvalue, right?
Yeah.
So if we only satisfy it when j equal to 2, then
J is equal to 2.
yeah, then should we also say that lambda is eigenvalue or not?
General is also eigenvalues. All the general vector is corresponds this only eigenvalue.
Yeah.
Because I have proved that it has these forms eigenvalue. Suppose we have m distinct eigenvalues. For each eigenvalues, we can compute this vector space. It's called null space. Okay. For maybe not a just this one. Together, eigenvectors.
That's the general eigenvectors.
Yeah. Okay. This is the general eigenvalue, and in the following, I will research some general eigenvalues properties. Because for each j, the general eigenvalues is null space of this one. Yeah, in the null space, and yeah, this one. This is the general value space, and And I'll prove that because
What did you want to prove?
no, I haven't proved anything.
No.
Just denote this.
Oh,
Yeah, the
I thought
value
you
is
want to prove
yeah.
something.
Yeah. I want to prove this one. Now space from the 0 power to the negative power along higher power. And this is I define the 0. Just if 0 power is this is definition is 0. So contourists can use some induction, and which is that if I can prove because this is I want to claim. This one proof and this is statement. First, if V is belong to now Tk, then it satisfies this condition in the null space is directed, and because this is 0 and use additional T operator, it has this one, and this is equal to 0, which is this one. So V is belong to null space for Tk minus 1, and so this exists because all the null space in the Tk also belong to Tk minus 1, null space Tk minus 1, so prove this one.
I think you didn't prove that k can be equal to 0.
Okay. Oh, that's because all the business space is 0 is belong to all the vector space, and which is because all the vector K belong to that one. Because first space just have 0. based on the previous statements, I want to prove it that if the null space for some faces M, for some position M, this the null space, the constitutive null space is equal, then all the after is equal to this space. The constitutive all the equal if they equal in some constitutive integers, this one. So the vector space is a set. How we to improve two sets are equal? We usually use this method for some constant, for some element from one vector, for two vectors, two sets. If we want to prove they are equal, we must prove that for all the E belong A, they must E belong B, and also E belong B. This is the unique method in set theory to prove the two sets is equal. Yeah. First, we have these statements for Tm they are equal. If we can prove this one, then it's done, I think. K is natural number. If I can prove this one, then I think I prove all this one. That's the logic from one. Because first, we do not need to prove is that is this because I have proved previously they are equal, yeah. And so I only need to for some element here, supposedly belong here, which is if here is the statement for each element in null space T M plus K and 1 is belong it has satisfied these equations, and so it can use some associated properties and have this one. So this one is in the null space T minus 1, which is this one, and because null T minus 1 is equal null T M for these statements here. First is so TKV is belong to null space TM, which means that this one exists, which means this exists. So for each so V is also belong to null space of T M plus K. So for each element that belongs to null space T M plus K plus 1 is also belong to null space of T power M plus K. So I prove that this two is equal. So I prove all these existed. And yeah, that's it. Based on the previous proof, it's easy to say that these are equal. If T is operator on V and this is V's dimension, that's because if they are if some are equal in the intermediate before dimension V, they are all equal because I have already proved that. If this cannot, then they at least increase one dimension at its belong one dimension. So it's all the dimension is dimension V. The null space can't exist this dimension. So it cannot. These two must be equal. This time, because this at least if does not exist in the intermediate, this increase 1 to 1 is 1. For here, the whole dimension is dimension V, or the null space is dimension V, and the null space cannot exceed the dimension V. So the dimension V minus 1 is also dimension V. So that's the problem. That's the whole proof, and I simply argue this theorem. We can, yeah. This is a general eigenvector definition, and previously I used T. Now I can use T minus I multiply I to denote the whole operator. And from the previous statement that all the general vector space is here, because this is from J to 1 to all. We know that dimension V is the final set, the biggest set. I have proved it. So all the general vector space is here. And all the class I want to prove that the operator even in LT, the M distinct eigenvalues is can decompose like this one. it's different from the spectral decomposition. It's a general decomposition. And to get this, we need to some previous establish some theorems. And based on this theorem, we can prove all the matrix. I said this for the self-joined, we can decompose the matrix like diagonal. But based on this one, we can prove that the general matrix can be decomposed like Jordan forms, which is that similar like.
So I guess the B is like basically the space spans by the B point B and the big B there, the big B, the same dimension B. Yeah, that one is the vector space spanned by like B1 to Bn. Is that?
V?
Yeah. How is it defined?
You mean how define V?
Yeah.
V is a whole space because operator is defined on vector space.
Oh, okay. B is the entire space.
The whole space.
So B1 to Bn is the basis also. So basically, you have that.
This is, you mean this one?
Yeah.
This is the basis of V.
Okay, so I can assume that the dimension of B is n also.
Yeah.
Okay.
So based on this one, we can have decomposed the matrix as Jordan forms, which is that its sub-block is like this one, eigenvalue, and this is one in the diagonal next to the mean diagonal axis. All the other position is 0. If you have lambda at different eigenvalue, you can decompose like this one, the block, the diagonal block. Yeah.
So that one should be null space of
This one?
about that should be null space of T minus lambda 1 I.
It's based on null space to establish some basis. Can you try exactly this one?
Yeah.
But I haven't reached this statement. Just the introduction, the final result.
Oh, so the condition above should have a null space like the direct sum of all these spaces.
In the null space of this correspond vector. But I should.
Because we didn't write the null space. Oh.
Yeah, this is the final solution at first.
I mean, about the nature.
This one?
Yeah, is that a null space of that? Is a typo there?
First, this vector I need to for the range, null space, we have this statement. This is the final. Yeah, this is the null space. This is the biggest set, and all of the belong is have the belong relation. Now I use the T just to show that this time. T star and. For the range, we also for null space we also have range. T star. What's the property it has this one? T0. Range T, range T is that we have defined linear transforms. TV, yeah. The equal width belong here. The range is all sets of this one. This is the range, and the null is this one to make is to 0 or the make it 0. properties of the mapping. For the operator, the V and the correspond mapping vector is the same, which is V is equal to W is V. And I define the range T0. T0 is the whole space. This is defined. For the null space, it is 0, and for range, it is the whole space. And have this relation. This belongs here, and which is also easy to argue. W will belong to range T minus 1. The W is for exists some vector V that its value is equal to W for the definition, and also extract as this one. And this one is in the range of Tm. So W also belongs to range Tm. So we have this relation. Based on the null space, I also prove that the range also has the properties. If M is bigger or equal to dimension V, we have this relation. It's based on this one. If the space is equal, we have previously proved this exists. The null space, the dimension of null space and range space is equal to the domain space I proved before. So condition we can transform have this one. And because null space if M is bigger than debate, we have proved that it's equal to the dimension of debate. And so use this again. We have this one. So if M is bigger than 1, the range dimension they are equal. Because they have the belong condition, if their dimension is equal, they are equal. For the belong, they have same basis. So I have also proved the range also have the similar property as null space based on this formula. And I prove the last theorem that we can stop. We already know that the matrix for complex vector space, I can choose some basis to make the matrix upper triangle. We can choose some basis that prove to make the upper triangle, and I want to count how many eigenvalues in this upper triangle here, and the conclusion is that there are this many lambda . Eigenvalue, eigenvalue, the diagonal matrix, the dimension of null space of this one. Generalized, this many eigenvalue here, and I will say that I only need to the eigenvalue of 0, because if it is non-zero, we can use this operator to prove there are how many zeros in the vector space. So I only need to prove the special case of 0. If non-zero, we can make some transforms like this one, minus some lambda I. Use the constructive method. I think it is hard. So first, I will define a space. It's v minus 1 from v1 to v minus 1. It's the subspace space of v. I use u to denote the subspace. And from this triangle matrix, we can also know that for V-1, we can have this expressed from the upper. We can see that. So this is a basis of U. So T is invariant on U. We can use this to express T. What invariant I will define. If V is defined on V, then U is a subspace belong to V, and for each element U belong to U, we have T. U also belong to U, then we call U is invariant subspace for T, because it's also defined a subspace and have a linear transform in the subspace. It did not have other vector to alternate to outer space, and we can define this one. So I use T U to denote the vector space. And for the basic situation, we know that I use the mathematical induction to prove. This is the basic situation for this one. The dimension is only one, and the matrix has a basis, only one basis, and expressed as this one. And this is the eigenvalue from this one. If lambda is 0, then this is equal to 0. So all the vector is transformed is 0. So the null space is equal to 1. Null space of T is equal to 1. And if lambda is not equal to 0, then this null space is 0. It cannot have a non-negative vector to map it to 0, because it's a multiply non-zero scalar. So it cannot be 0 here. This is non-zero. This is non-zero. It cannot be 0. So the basic situation is that for this one, here correspond this one. If it's 0, it has a 1 0, so it is equal to 1. If it's not 0, it do not have 0 in the matrix, and so the dimension is 0. And the basic situation is correct. Now I will make the induction. This is the basic situation. Because I make the induction is that I suppose if n is if the situation is n minus 1 exists, I will prove the n. I will use the n minus 1 to prove n, and so I think I can use here is that I suppose lambda is 0, so this can be raised here. Because I will argue if not 0, I can use the T bar to argue, and this T star has the eigenvalue of 0. So we can use the just case when lambda is 0 situation. Let me see how many. There are this many lambda that equal 0 in this diagonal from the induction. This is operator, and the dimension of this one is n minus 1. The dimension is dimension v minus 1, and the operator's power, and so. Because this exists, as I proved before, the whole dimension of U is dimension v minus 1. So I have proved before it's also equal to this minus 1. It's equal to null space with U dimension v. And so in this situation, I will divide my proof into two parts. First, I have already to induction is that all this eigenvalue is equal to this one, and what I want to prove is that all these eigenvalues is equal to this many. So this some previous argument. If lambda n is equal not equal to 0, these two must be equal to make to complete proof. If lambda is equal to 0, then this one must be equal to this one plus 1 to complete the proof. So I divide it into two parts. Right here, statements. Here. this one. And which means,
Excuse me, it's line of null what
this one,
is T.
this TU is the operator on U, the subspace. Because the subspace is invariant, I can define a mapping based on the subspace. Okay? Yeah. Here, we want to n minus 1 it's a triangle upper matrix, so it's have not other vectors split to lambda n minus 1. So it can define this vector space. And so if I can prove this one, now space of T dimension belong to U, then they are equal. Because this, yeah, see this space. Because it is a triangle matrix, and its k, its power of k, the expression can be like this one. Because the triangle matrix is multiplied together for the diagonal, just as the same power. And this may be different, I don't care. But this is 0 for the triangle matrix. It's the same, they multiply together. And it has these forms. for the general vector, it can be expressed as this one. U is belong to the subspace. This belong to this subspace and have additional Vn from here. So this A is the scalar. For the general vector, it can be expressed as this one. If in this null space, which means that this space, if it is a null space of Tk or dimension V, I use K to dimension V now to express. And if it belongs this dimension Tv, this is equal, means this is equal 0 null space, yeah. And we have these forms. It use some because Tk is also linear operator. It can be we can draw out of this A and U, yeah, like this one, from this one to this one, and also from these forms we have Tk Vn is equal to this scalar multiplied this one. This is belong to U because the forms and plus Vn multiply lambda n k, and so it have these forms, which is have these forms because it is equal to 0. Because U is invariant on T, so this is also belong to U, and this is U. Tilde is also plus A is also belong to U, and this is belong to V. They are from different scalars too. So if this equal 0, this must be 0, and this must be because so they are independent. So this must be 0, this must be 0 to make the independent. And because lambda nk is not equal 0, lambda nk. But lambda n is not 0, so lambda nk is not equal to 0. And Vn is not 0 because it's basis. So A must be equal to 0. So if A is equal to 0, so V is equal to U and belong to this one, the U. So I have proved that this space is belong to this one. Is belong to U. Is in the null space. It must belong to U. So this is the case for the lambda is not to 0 cases. Just use the linear independent to construct this vector. If lambda is equal 0, here we have additional, we must decrease 1. So I must prove that null space Tn is equal to the subspace plus 1, because I will prove lambda is 0. This is in the matrix, so they have more appearance on the matrix. So for the 0 situation, it must prove this one. Let's review some lemma. I think we all have proved this theorem. For dimension, the two space they added together and is equal to this one. The dimension is the relation. It's easy to, like a set operation, it's easy to understand. I also prove. I remember I have proved this theorem. And I use this theorem to prove the previous to prove this one. If I let U is equal to null space of Tn, W is equal to U. This U, this V, then I can put these atoms to here and to have these forms like this one. Which is equal to this one. Because the null space Tn is all belong U, so it's in the U subspace. You can use this to describe this meaning, which is this one is equal to this one. And because U have dimension of n-1, so it's just n-1. And so here I want to say that so I have one element, I found one element in the null space, for example, some null vector here. I found the vector. This is construct method. It's hardest. If I found V is belong to the null space Tn and V not belong to U, then I have the following statements. Because the whole space have dimension of n, the null space and union the subspace cannot exist than the whole space. So this exists. And also, if I can find some vector in not Tn and not in U, then this dimension space must be bigger, strictly bigger than the single space of dimension U, because I found some vector not belong to U here. And the dimension of du is equal to n-1. And so this, we can we can get is equal to n. Yeah, because it's bigger than n minus 1 and less or equal than n, so this must be equal to n. And it's this one. If it equals to n, then n minus 1 is equal to 1. So it's like this statement: 1 minus this one is equal to this space. So if I find the what I need is that I must find one vector which is belong to non of Tn but not belong to U. Then the proof exists. This is the constructive and find one vector. So I will find this vector. That what I can constructing the vector is equal to some u minus Vn, and this is in the non-zero Tn. So Tv like this one it must be 0, and it can be like this one use additive property of operator, which means that Tvn is in the range of Tu n. Yeah, here. Yeah, this is all equal. If I want to find this one, I need to find this one. Because Tvn is belong to some u. That's because lambda n now is 0, which means that Tvn Vn is equal to V1 A V2 A2n. Yeah, TKVn can be expressed like this one. Now the ANN is lambda n and equal 0, so the Vn the Vn do not have Vn in the Tvn, Tkvn subvector, do not have this vector space because N is 0. So, and all previous vectors belong to U. I have already defined the previous vector. So, Tvn is belong to some U, and so Tn Vn is belong to, which is equal to T minus 1 T V. This is belong to U, so this is in the range of Tu minus 1. And I have proved that the whole space of U is dimension is n minus 1. So it's equal to this one. So I have proved that the Tvn is in here. So this equation is equal, which means that I have found the vector, some vector which is belong to not with Tn but not in U, and so this exists. That's the I prove this one, and I mentioned some definition. Yeah, for the here, I have proved that the matrix here exists on the diagonal axis. We call this one is a multiplicity of some lambda. It's a multiplicity. I have proved that it is just equal to this one. N is equal to dimension V. The multiplicity of each vector is equal to this one. And this multiplicity, we define the characteristic of the this is the character for each eigenvalue. We have multiplicity, and I define this polynomials as the characteristic of this operator on this space. Also have for matrix, they also call this multiplicity characteristic matrix. For the polynomial characteristic polynomial of the operator, it have some interesting properties such as Cayley PZ, such as Cayley-Hamilton theorem, which states that PG is equal to 0, zero operator. It's easy to prove based on the previous statements. How interesting I can